In this lesson, we will look at global climatology. We will build a model of the large-scale processes that work across the planet. From these processes, we will be able to identify large-scale pressure systems, surface winds, and eventually weather patterns. These weather patterns will be split into specific climatic zones which contain unique weather characteristics. Looking at the diagram, we can see a view of the Earth split north-south. Using this picture, we will construct and build the model of global climatology. The most fundamental aspect which controls the weather processes is the global air circulation. We have seen these air circulation cells already in other lessons, but we will expand and explain them in detail here. The diagram shows that the Sun's energy is coming in at an angle of 90 degrees at the geographic equator. It is therefore this region that will receive the greatest amount of incoming solar radiation. As the land is warmed, the air in contact with it will also be warmed by conduction. This warm air rises through the atmosphere and eventually diverges on reaching the tropopause. As this air moves north and south, it eventually cools and descends. When reaching the Earth's surface, some of this air will return to the equator again and complete the circulation of one of the two cells. These are called the Hadley cells. They are the warm air circulation cells that will always be centered around the point of maximum heating, in this example, the geographic equator. But remember, the point of maximum surface heating moves north and south throughout the seasons. Now let's examine the airflow over the polar regions. The air here is very cold and tends to descend. As it descends to low levels within the troposphere, it diverges from the poles and moves steadily in the direction of the equator. This descent and divergence causes high pressure to build at the poles. At this point, we need to bring in the rotation of the Earth. If the Earth were still, the circulation would be like this. However, the circulation is complicated by the Coriolis effect, and we end up with three distinct cells like this. These are called the Hadley cell, the Ferrel cell, and the polar cell. The actual pattern of airflow is very complex, but this is an idealized model and as such is kept very simple. Remember that it is these cell circulation patterns that are the foundations of the global climatology model being constructed. From these patterns of global airflow, it is possible to identify large-scale pressure systems. Let's take a look at the junction of the two Hadley cells. Notice that the airflow at the surface is converging and rising. Eventually, this air diverges upon reaching the tropopause. This pattern of airflow creates a net loss of air in the region shown. This is because the air at the surface is entering more slowly because of surface friction. But the divergence of air at the top is much more active due to the lack of friction. We have learned from previous lessons that a net loss of air reduces the weight of the atmosphere against the surface. Therefore, a low pressure zone is created. This belt of low pressure is found all across the Earth and is called the Equatorial Low Pressure Belt, or the Intertropical Convergence Zone, the ITCZ. As we have already mentioned, this zone will move north and south as the point of maximum heating changes from season to season. But for now, let us assume it is stationary near the geographic equator. Looking at higher latitudes, we can examine another zone where the airflow is very similar to the equator. In other words, at the surface, airflow is converging and rising. Then, upon reaching the tropopause, it diverges. This location forms the second major zone of low pressure. This band of low pressure is known as the polar front, and the depressions created are called the polar front depressions. They are also called the temperate depressions or the travelling depressions.